All right, so we're back, and in this section, we're going to talk about the chronometric studies of imagery. You know, during the Galton, Wundt time period where people were using introspection, there was a lot of complaint that individual differences might be overstated or might be understated as a function of how people were describing their internal experience. So a push was on to try and figure out a way to measure internal imagery in a more objective way, right? In a more direct way. So chronometric studies came along. So chronometric literally means time measuring. Chrono means time and metric means measuring. So we're going to use time to try and measure the type or style of image that a person's holding. So, what they do in these chronometric studies is ask participants to judge or manipulate the mental images that they form to different kinds of stimuli. And then we're going to measure how long it takes to make this judgment or to make this manipulation of the mental image. And that's going to allow us to test the different hypotheses that have been proposed in this field. So, in general, chronometric studies have shown us that mental images are picture-like, that people actually scan them and manipulate them. So going back to 1976, Koslin had participants answer yes and no questions about their mental image that they formed to some kind of stimulus. And so in the case of an imagined cat, so the prompt is imagine a cat. And now I'm going to ask you a series of yes/no questions. What they found is that it was easier, therefore it went faster for people to confirm to say yes, the cats have heads, than to say yes, cats have claws. This is when a person is holding an imagined cat in their mind. It takes longer to say that a cat has claws than it takes to say a cat has a head. And this is just yes, no, to agree to that or not. So now if instead of being told imagine a cat, they're told think about cats. Okay, so I'm not necessarily going to spontaneously generate an image of a cat when I'm told to think about cats. I might think about the category of cats, and I might think about the characteristics that the category of cat might have. In that circumstance, when we take out the imagery part of it, we find that people actually confirm that cats have claws faster than they confirm that cats have heads. Now, if you remember back several chapters ago, we talked about this kind of categorical processing, and that, you know, if it's true that you have information organized in your brain in sort of this hierarchical way, so that like under the category of animals, all of them would have heads. But under the category of cats, now we have claws. Like not all animals would have claws. You'd have cats might have claws. You might, what else has claws? I'm blanking on it. I actually watched an episode of Family Feud, and one of the prompts was animals with claws, and like lizards have claws. There are a lot of things that you could have under the category of has claws. But it would be a longer trip up the hierarchical category to confirm the existence of a head than it would be to acknowledge the existence of claws when you're given the prompt to think about cats. So there's something about imagining a cat that reverses that. And the idea probably is that when you imagine a cat, you are looking at a cat and the head is going to be quite noticeable, right? It's a prominent part of a visualization of a cat, an imagination of a cat. Whereas if you're just thinking about the category of cat, head is sort of taken for granted, don't you think, right? You sort of assume that animals have heads. So the other thing that Koslin noted back in 1976 is that the pattern of available information changes as the mode of presentation changes. So here we have an example where the participants were shown this map. And I think this map is replicated in your ebook. So they were given this map and they were allowed to study it. And just to draw your attention to it, you know, I'll start at the bottom right-hand corner. We have a beach, right? And then you kind of go around and you see this little hooked area that implies we might have a little cove or a harbor, an island off the shore, right? So you kind of go around, you see that there's the pile of rocks on the top. You've got the grass field here, a tree, a lake, a hut, a well, another harbor probably on this side. So you have these like sort of landmarks that you can latch your memory onto to help you to visualize the different components of this map. So once the participants have memorized the map, they ask them to visualize moving between places on the map. And this is what they call an image scanning procedure. So they memorize the map, then they're told to imagine the map. So visualize in your head the map, imagine it. And then imagine a black speck moving in a straight line from, let's say, the hut to the hooked harbor that's near the island, right? And so you'd have to imagine making that travel, or imagine the black speck moving from the hut to the well, these kinds of things. So that's what we call an image scanning procedure. It's an image that's being held in their minds, and then they imagine that they're moving through that space. What they found in this, what's depicted in this graph, is that the farther away the items are on the actual map in distance, this is in centimeters because of course the map is just a drawing. So the farther away it is in centimeters on the actual map, the longer the response time, right? So things that are closer together, hut to well, is going to have a quicker response time than, let's say, hut to pile of rocks on the far end of the island. So the farther away they are, the longer it takes to respond, implies that the person is probably visually scanning the image that they're holding in their head, that they are literally imagining what would it take, how far would it be, and they're somehow measuring that in an imaginary way. So it takes time to mentally scan a mental image. And that's how chronometric testing works, is that it does take time and we can measure that. Now, of course, this technique really could only evolve once we had the correct kinds of measurement tools to be able to make this possible, right? So by 1973 in this study, no, this is 1983 when Kostelin did this one, and 1976 when he did the earlier one, there were tools available that could measure time, to a tenth of a second. We, have them for the Olympics back then. So certainly we can measure time very accurately. Today, we could probably even do a better job with even faster measurements. So we might be able to get it down to the, 1,000th of a second as opposed to 1/10 of a second that you're seeing here. So by using these techniques, we can say a person is scanning an image that they're holding in their memory or they're holding in their minds. Here's another example of that. So the participants are shown a picture like this, and then they're asked, the picture is taken away and they're asked to just visualize this picture. Where's my prompts? Sorry, my animation's messed up. So the question is, does a mouse have whiskers? I'm going backwards. I was watching somebody else give a talk and panic and push the wrong button. So I feel a little bit better about doing it because you do kind of panic. Why am I not pushing the right part? Okay, so let's say in this picture, you're asked, does a mouse have whiskers? You're holding it in your mind. You're not looking at the picture. You're holding it in your mind. There's a delay, almost as if it takes time to zoom in from this larger picture that could include an elephant down to small enough, close enough that you can actually see the mouse and detect whether he has whiskers or not. Whereas if there's a picture of a mouse and a paperclip, you're going to have a faster reaction time because you don't have to do that zoom part, right? Because you're already close enough that you can visualize the mouse without having to zoom in. So response times are directly proportional to the amount of zoom required. The more zoom, the slower the reaction time. So elephant next to it takes longer to confirm that a mouse has whiskers. Paperclip next to it takes less time. All right, and then here's another chronometric study where we are going to measure how long it takes a person to do the task. Again, my animation's messed up because the brain shouldn't be there yet, but just ignore them. Okay, so in a mental rotation task, you are asked whether the shapes in each row are identical to each other. And I can tell you on this particular one, so you don't stress or strain, that all three rows contain identical objects. But in real life, in this kind of study, they would have some of them would be the same object, just rotated, and some of them would actually be different objects, and you'd have to really study it to figure it out. And we call this mental rotation. Can you mentally imagine rotating the object on the left in each row and resulting in the object on the right? So the angle of rotation is directly related to how long it'll take you to answer the question. The less rotated, so down here, if you're at 0 rotation, that means it's the exact same position. Yeah, it takes you no time at all to respond. Just the normal amount of time it would take you to utter a response. But the more rotated, 180 means it's twisted exactly the opposite direction, right? The more rotated, the longer it takes a person to be able to confirm or deny whether those two objects are the same. And what this is showing us down here at the bottom is that it's the back part of the brain that's mostly going to be active because that's where the visual processing is. So you see a lot of activity in the back part of the brain. But you see more activity when the object is rotated 120 degrees than you see when it's only rotated 0 or 40 degrees. So the more different the two objects appear, the more brain power it takes to actually answer the question, are they the same or not? So mental rotation tasks show us that it takes longer. And then, so the chronometric measurement shows us that it takes longer to do these mental rotation tasks. And then functional MRIs show us that it actually takes more brain power to answer the question the more rotated it is. All right. So imagery and perception. Visualizing and perceiving rely on similar mechanisms. So you recall back from earlier chapters, we talked about perception being your brain making sense of what's coming up from sensation. So as the information comes in, your brain figures out, have I seen this before? Is it something that I know? What could it be? It's making all these guesses to try and figure out what the sensory organs are sending out. So one of the things that researchers have shown is that if the stimulus is presented quietly or it's in dim lighting conditions, the visualized version of it, if you ask them to imagine the thing that I just provided to you, it will also be quiet or it also will be dim. So your imagery is very similar to what was actually presented. And as a result, it takes you longer or it is harder for you to actually detect the details because it's kind of dim in here or it was played so quietly. So even the imagination is going to be incomplete in that way, right? It's going to be harder. So for visual and for auditory, we see the same kind of pattern. We also see one of the patterns that we've talked about before in class, which is priming. If you're expecting to perceive something, you will do it faster when that stimulus actually arrives than you would have if you weren't expecting it. We see that in imagery also. If you imagine the object before presentation of the actual object out in the world, you will perceive the real object out in the world faster than if you hadn't imagined it beforehand. This always brings to mind, like sports psychology for me, where if you visualize it before you play the game, then the behaviors that are necessary for success come to you more easily, right? So if you just sort of visualize it beforehand, you will perceive that object more quickly. Like I showed in that fMRI in the last slide, the same occipital areas that are used for actual visual processing, especially the early visual processes, are the ones that are also active when you're visualizing something. And so your brain doesn't seem to necessarily care whether it's a real stimulus or an imagined stimulus. Here's another version. This is actually from, I think these are PET scans. I don't know. Those do look a lot like fMRIs because you see a lot of D. So it's like an MRI that is colorized kind of strangely is all I can say. And what you're seeing on the top row labeled A, it is a person actually perceiving faces. and places. And faces are easier and have more activity than places. So you see perception on the top row, and then look at the bottom row B, where you're imagining the same thing. So the brain in the top row A is seeing the same or experiencing the same thing as an actual perception that the same brain below it is doing in row B, just imagining it. And so you see look at the second one in from the left. Let's see if I can point it. If we were in class, I'd be pointing at it. But so hopefully you can see my arrow. So you see this little area of activity on this brain here. It's a little smaller in the imagery. And notice on this next one, same area, little smaller. But then on the right side, you don't see any activity on the imagery. You see it on the, and this is faces. You don't see it on the imagery one. That face recognition area that activates in a real perception doesn't activate in the imagery. So you'll see that's different. And then on this far right one, there's again that bigger dot on the top of activity. It's just a teeny tiny dot on the bottom one. And then here we have the same kind of thing going where places comes before faces. And so now here's what we see here. So the premise I'd like you to get is that the brain activity is similar, but it's not identical. Now, some people have wondered, would we be able to tell a person who's describing a true perception, like maybe they're currently looking at it and they're describing it to us, versus a person who's just generating an imagination and telling us a story about it? Would we, let's call it the first one truth telling and the second one lying. Would we be able to tell truth telling from lying just by using functional MRI? And I don't know about you, but from these similarities, I wouldn't feel comfortable accusing somebody of lying because their brain doesn't have activity on the right side or something. I wouldn't feel comfortable with that at all. So we're not there yet where we can tell whether a person's telling the truth about something or not. But we definitely, there are a little bit of differences, but there's an awful lot of similarity between the perception and the imagery. All right. I'm going to go ahead and stop here and we'll come back and talk about spatial images versus visual images. All right. See you then.